So, so today I won't have time to do the recap, but just to remind you what we were doing last time was basically, I mean, we did the field theory or functional integral to calculate the density of states, the global observable, and then we looked at the distribution of some observable, which is this linear statistics. Meaning some observable which is of this form. I gave you one example, which is total number of positive eigenvalues, where the function f of lambda was just a theta function. And given the joint distribution of eigenvalues, which is always this form, or in general v of lambda, and plus so given this joint distribution, then you wanted to calculate the probability distribution of this observable A for a given n. And generically, we saw that this is of this form, some beta n square into some kind of large deviation function that depends on the observable A. Okay? And we saw that at least for the case of theta function, this object there has a non-analytic singularity exactly around its mean point. It's not completely Gaussian. Okay? And so this general procedure holds for any arbitrary potential and any linear statistics in general. Okay? I just showed you some example. And thanks to the so what happens is that this linear statistics, when you put a delta function, this just modifies the effective potential. And since in general you know the Tricomi solution for the integral equation for the saddle point equation for arbitrary potential, so therefore, in principle, you can actually solve and calculate the large deviation function. Okay, so that is what we did. And near the end of the talk yesterday, I was talking about the largest eigenvalue. That means you take these charges, lambda 1, lambda 2, lambda n. So lambda n is the max, I mean, this is unordered. So you define the largest eigenvalue, which I'll denote by lambda max, which is the maximum of all these guys. So this is also a random variable, but notice that this is not of the linear statistics form. Okay, it's a nonlinear function, you know, generally like this. So I can't really use this technology here. So I have to find out some other way of calculating the probability density of lambda max. So little p here means probability density. And I'll also denote by capital L as a cumulative function. So this is the probability that lambda max, so let's see, p of wn will be the probability that lambda max is less than equal to w for a given n. So if I know this cumulative distribution, this capital P, then the little p, probability density, you can derive just by derivative, because by definition, this is minus infinity to w, p of whatever, little w prime n dw prime. This is a cumulative probability that all lambda max is less than equal to w. So if you know the probability density, to integrate up to from minus infinity to w. So if I take the derivative of that, then I can get the probability density. So this guy is normalized to unity. So you know, when you plot a cumulative distribution, so how does it typically look like? Somebody tell me, please. Any function, any random variable. So we plot versus w. So what happens when w goes to infinity? One. Okay, this is normalized. So if I plot the cumulative distribution, when W goes to infinity, it always goes to 1. So PWN, so little, this is the probability density. So it might, it might look like something like that. But when you integrate, that guy typically looks something like that. When W goes to minus infinity, it goes to 0. And when W goes to plus infinity, it goes to 1. So this is a useful picture to remember, okay? So all of you know this, very basic. But for any random variable, the probability density function is usually typically azipic, like a Gaussian function, for example. But cumulative distribution always has this knee structure. It saturates to 1. So we would like to calculate now this object, cumulative distribution. It's easier, okay, than the probability density itself. Sometimes, okay, we'll see later that this might be useful also. So my task is now, given this joint distribution, okay, so this is the JPDF, joint probability function of all these guys, and then I have to compute the distribution of lambda max from this, okay. So the task is to compute, if I can compute the cumulative, I can compute the density by taking derivative. So compute this from the JPDF. Yeah, I give you this, you compute that. That's the task. Now, before I do that, so let's just take a back seat and ask, why am I interested in this lambda max? Okay. So what's the motivation for looking at this problem? So the motivation actually is very nice, and it goes back to what is called the linear stability problem. So let me just tell you a little bit about that. Let me remove this first. Just remember these two pictures here. So he wrote a paper called "Will a Large Complex System Be Stable?" This was published in Nature. This is a reference. This is a very beautiful paper. Everybody should read this paper. Very simple and nice paper. It's one of the few Nature papers that you can read and understand. Okay. So what May was interested is in the following problem. So imagine that you have some kind of ecosystem, okay, some forests, let's say. So you have different kinds of animals, tigers, I don't know, lions, human beings, all kinds of things. And so let's say rho I is the population density of the ith species. Okay. And to start with, imagine that they are completely non-interacting. Okay. They talk to each other. Tigers are with tigers, lions with lions. And each of them are stable. What do I mean by that? To start with, stable, non-interacting population. What does stability means? Meaning, if you make a small perturbation, so they have an equilibrium value, let's say rho I star, let's say 100 tigers, that's typical value. And the tigers are dying and taking baths, so they have a steady state value, which I call stationary value, which I call rho I star. So stability means that if I make a small perturbation, okay, around the equilibrium value, okay, let's say we generate some more tigers, okay, Then somehow the birth and death process, this will be a stable, means that this deviation from the equilibrium value will decay exponentially fast in time. Okay. For example, something like that. I set the time scale to be 1. Okay. So which means I make a small perturbation, okay, and it just it's like a harmonic chain basically. So it's just not harmonic chain. It's like a sitting in a potential, quadratic potential or something. So dxi, so which means that xi will go to xi0 exponential minus t. So exponentially it will decay to 0. So that means exponentially fast it will come back to its stable value. Okay. So I start with this. Okay. So stable, non-interacting, and non-interacting because here it does not involve any other species. It's just within itself. Okay. So imagine that you have this. Just represent this population by points like a node. In general, I mean, there's no concept of space here. Okay. So these are different species. Okay, tiger, lion, humans, I don't know, birds, and so on. Okay. So you have all these things. Each of them is a stable population. Okay, so they are just fluctuating around their equilibrium value, and very quickly they come back to its equilibrium density. Okay, so they are stable system to start with. So now, what may ask this following question: imagine now switching on the interaction. Random interaction. I'll tell you what it means. It's a very simple model of population dynamics in a disordered sort of kind of interacting system. So what this means, switching on the random interaction, is that he writes now the equation of motion of the deviation from the stationary value to be of this form. So as before, you have a part which tells it to, without interaction, it will go back to 0, and then you add a term here, which you write down something like this, sum over all j. So this is the interaction term. It says the pairwise interaction. So, you're just putting from each I, you are putting a node, interacting node to all the other guys. Okay, this represents these links represent the interaction aij. So this is supposed to be a random matrix, and this alpha is called the strength of the interaction. Okay. So when alpha is 0, so clearly they are stable. Now you switch on this interaction, they start interacting, everybody starts interacting with everybody else via this matrix aij. And you ask, so you have a complex web of system, and you ask, are they going to be stable? Meaning that are all the xi's going to go to 0 as time goes to infinity? Okay. It's not completely obvious, right? If alpha is 0, certainly they are stable, but I switch on the interaction and ask what is the effect of interaction on the stability of the system. Okay. So I want to address this problem. Yeah. I mean, there is a diagonal term which is like a self interaction, if you like. You can throw it away or if you like, but just keep it, simple model, just whatever. You say, okay, I mean, that will just renormalize this rate here, okay, the diagonal part, so not change. So that's the question you was asking. Will a large complex system be stable in presence of this interaction? Okay. So what he found is quite amazing, quite interesting at the first sight. So the question he's asking is, what is the probability, stability? Probability, because now this this matrix Aij is a random matrix. Okay, so for each realization of this matrix Aij, you have either the system will go to 0 or non-zero, maybe stable, maybe unstable. So this is a random matrix, and he took the simple model where it's just same thing, this Gaussian random matrix that we are talking about. Okay, that means trace of S square, which means basically you just take each element as independently Gaussian real symmetric matrix. Okay, so it's a product of all the individual elements. So you just assume each link is a Gaussian random variable. Okay, so it may be positive, negative, and so on. And so this is the matrix he was interested in. And then what he was wanted to compute is what is the probability. So that's where probability comes in. Okay? So what is the probability that the system remains stable once the interaction alpha is switched on? The stability probability. So how will you solve this problem? So first thing, notice this question is actually, you can write it. So if I think of this x size as a column vector, okay, so this says ddt of this vector x, you like. So vector x means just its entries are, it's a vector, so it's x1, x2, x3, xn. So you see, I can write down this dx dt. Let me write it this way, vector like this. So this is just, I use the matrix notation, alpha A minus identity matrix times. Is that clear to everybody? Just think of this as a matrix. So alpha A minus identity. So that's the matrix. So I'm just writing down this as, another matrix Mij xj. So this matrix M is just alpha A minus identity matrix. Okay. So what's the criterion stability? What's the criterion for stability? The criterion for stability. So I can diagonalize this matrix by orthogonal transformation. So if I diagonalize, so then you see that this. So I may make an orthogonal transformation. That means I go to let's say y as Sx, where S is an orthogonal matrix. Okay. So once I diagonalize this, so then the y vectors, they are diagonal. So, okay. So alpha times the diagonal part minus identity. Clear? So this is just the diagonal matrix, which is lambda 1, lambda 2, lambda n, which are the eigenvalues of A. Is that clear to everybody? Fine? Just diagonalize this matrix, okay? I mean, you have this matrix Mij, which is this guy, so you make a diagonalization. So that means basically it says that dyi dt I minus 1 times yi. That's all it says, okay? So the stability for criterion for stability is that all the yi's should go to 0 as t goes to infinity. Only then the system is stable, which means that this guy should be negative for all I. Right? for all I, this is a negative object here, so again it will exponentially go to 0. The system will remain stable provided this criterion holds. So this criterion means that each of the lambda I should be less than 1 over alpha for all I. And let me call this inverse interaction as W. So therefore, what is the probability that the system remains stable once the interaction is switched on is exactly equal to the probability that all the eigenvalues are less than equal to W, where W is 1 over alpha. Okay. Which is indeed the same as probability that the largest eigenvalue, lambda max, should be less than equal to W. So if the largest eigenvalue is less than 1 over alpha or W, then you are ensured that the system will be stable. Okay? So he did not calculate this, but what he kind of conjectured, and actually he kind of argued, is that if you now plot this stability probability as a function of W, which is the inverse interaction strength, what I'm plotting in the y-axis is the probability for the system to be stable, which, as we saw just now, is the same as the cumulative distribution of the maximum, right? So this is exactly the cumulative distribution that we defined, capital P of Wn. So this is the probability that the largest eigenvalue of the matrix A, interaction matrix A, is less than equal to W. So if you plot this P stability probability versus W, what do you expect? When alpha is 0, that means no interaction, we know that the system was stable to start with. So the probability that the system is stable is 1 if your alpha is 0, which means W is infinity. So when W goes to infinity, it should go to 1. Here it's 1. So that part is clear. And what May found, so the system here is stable. He found that as you decrease the interaction strength, as you increase the interaction strength, that means you reduce the W, the system actually remains stable till a particular critical value of the interaction strength or inverse interaction strength W, C, which is √2. So it remains stable like that, and then shook in the large n limit, in the limit n going to infinity, it becomes 0. So this is the unstable phase. So there is a phase transition in the system. Okay. So you started out, you switch on the interaction. So as you increase the interaction strength, the system is still stable. There is a critical value WC equal to √2, at which, so here I set beta equal to 1, at which it just sharply, it just immediately becomes unstable, okay, for W less than √2. Okay. So this is called the May phase transition. So this is the between the stable phase and unstable phase. Okay. It's a sharp phase transition in the large n limit, okay, strictly in the n going to infinity limit. We'll try to understand this in a minute, where this comes from. He has some argument, okay, we'll see that argument in a minute. So, right. So now, question is, what happens for finite but large n? Because the n going to infinity is a very special limit. Usually you have very large population, okay, n is large. So so what happens, so question, what happens for n finite but let's say large? So what do you expect? So what would you expect is that this sharp line here will be replaced by some kind of crossover line. Okay? So for finite n, there will be a smooth function like that. As you take n going to infinity, it's like a typical any phase transition. As you take n going to infinity, the limit, so this guy finally will become a sharp theta function. So the problem then was to compute the finite but large n part of this curve, okay, phase transition, and therefore you are interested in calculating the distribution of lambda max for a n large but finite. Okay? So that was the motivation. So what can we say about this curve? And what I want to show you today is basically how to describe this curve. And what we'll see is that there are three regions, three parts to this curve. There is a central regime, which is just around the transition point, okay, whose width will be of order n to the power minus 2/3. And then there is so if you plot the derivative of this, that is PDF of lambda max, okay, this is the p, little p of Wn. So what it says is that strictly in the n going to infinity limit, if you take the derivative, it will be a delta function around √2. Okay, so delta function around √2. But for finite n, this guy will have some width. So this dotted curve here will correspond to some dotted curve there. I should draw it with yellow. This one is just the derivative of this curve, okay? So what it says is that this region width here, so that means this region will be of order n to the power minus 2/3. So it's a very narrow region for n large but finite n. And as you increase n, it becomes more and more like a delta function and approaches to this curve or delta function there. But there are two regimes to the left. So this I'll call the central regime, which is around the peak, basically, of the PDF. But there are these two tails here, one on the left, one on the right. Okay? And here we'll see that the behavior will be completely different from the central regime. So these are, what is called the large deviation regime. So this is in the same spirit that Kiran has been talking about. But we'll see that again this large deviation, so this is, I'll call the left large deviation, that is this part of the curve, and this is the right large deviation. And we'll see they have very different behavior, okay? I'll try to understand how the left and right behave and how they match smoothly with the central regime. So the central regime, this part of the curve will be called what is called the Tracy-Widom part, and then there is a large deviation tails on either side. Let me draw it white, and this is maybe with yellow. So this is the right tail. This is the left tail. And this will be called Tracy-Widom. So I'll describe this in a minute now. But before we do that, just to appreciate this different regime, because it's quite important to understand the scales here, different scales, okay? So in order to understand the physics of this problem. So for that, I'll go back to a toy model that Kiran already described to you, which is just to understand the large deviation. I'll just repeat what he said, just to put it in this context, so that you know what we mean by large deviation and what we mean by typical and so on. What happens typically in a typical system, and then you'll see how different it is in that problem. So this is the problem that Kiran described to you. This is just 1D biased random walk problem. This is a standard example that everybody uses to understand large deviation. So let's say we take it on a lattice with unit lattice spacing. I start a particle at the origin, and this particle with probability QP, it jumps to the right. With probability Q, it jumps to the left. With P plus Q equal to 1. So Kiran was doing in continuous time Markov process, but here I'll just do discrete time. It doesn't matter really. So this process, of course, you can write down the master equation and things like that. But another way of looking at it, if I'm just interested in the position of the particle, so if I write xn, which is the position of the particle at step n, so how does it evolve? I mean, if you are following one particular history of the evolution, you can write an analog of Langevin equation, which says that the particle position at the nth step will be whatever the particle position as n minus 1th step plus a jump. So plus a jump, which I'll denote by eta n. So this eta n is a random variable. And what is the distribution of this eta n? Since I'm taking a binomial random walker, so this means it's probability half, or no, actually in general, let's say with probability p, it's eta minus 1, and with probability q, it's eta equal to minus 1. So this is just says that this distribution of the noise is either plus 1 with probability p or minus 1 with probability q. So it's just this picture here. Okay? And you started with x naught equal to 0. So you immediately see that if you iterate this equation, you can write down xn as a sum over all eta k going from 1 to n. Okay. So let me denote this by, I'll denote it by m in general. M is means position of the particle after nth step. So m is a random variable, and it's a sum of independent random variables. So these eta i's are independent and identically distributed random variables. This is usually called IID. Okay, so then you know how this M will behave, because all of you have heard of central limit theorem, which says that if you have a sum of n independent variables, then the distribution of M is going to be Gaussian, okay, over a certain scale. And so for Gaussian distribution, all you need to know is what is the mean and the variance. So calculate the mean. So clearly average M is going to be the average of each of these guys. So I have P of eta, I can calculate the average of eta. So average of eta will be, tell me. Your P of eta is this. What's the average of eta? This is integral eta P eta d eta, right? This is just P minus Q. Okay? So what you have is, this is the overall bias with which the particle is moving to the right. So therefore this is P minus Q times n. That's the average. And what about the variance? Anybody? Variance also you can calculate, just take a square and use the fact that they are independent of each other. I'm not going to do the calculation, but you can check that this will be just 4 P Q n. Okay. So therefore, it says that if I look at the central limit theorem, tells me that the probability distribution of the position of the particle after n steps, where n is large, okay, it should go to a Gaussian distribution with this mean and variance. Therefore, it should go to e to the power minus m minus p minus q n square divided by 2 times the variance. So therefore, it's 8 pq n. And okay, you have this factor here, which is 2 pi times the variance for PQN. Okay. But is it true for all values of m? No. Okay, another way of writing this is to say that this random variable m, so it goes to its value p minus q times n. Okay, so this is the mean value, and there is fluctuation around it, and the fluctuation is precisely the square root of the variance, which means 4 pqn times a random variable which is independent of n, and this random variable chi has the PDF, which is precisely Gaussian. So if I plot this function, okay, so its mean value is p minus q times n. So I'm plotting it as a function of m. So it will be picked around its mean value, m minus n, and it has a Gaussian peak around it, and the width of this peak is of order square root of n. Okay? So the mean is going linearly in n, and the width of this distribution around the peak is going like square root of n. Okay? But this is valid only not all the way till the end. See, the m, which is the position of the walker after n steps. So what's the maximum value of m? M has to be between, tell me, plus n and minus n. Okay? So I have a limit for any finite n. The m can go up to plus n. So I'm plotting, this is the m axis. This is the mean here. And maybe here it's minus n. So m has a range from minus n to plus n. It cannot be more than that. So around the mean p minus q times n, it has a Gaussian distribution. Okay? But is this Gaussian form valid all the way until the end? The answer is no. Because, for instance, just to see one example, suppose I want to calculate p probability that m equal to n. What's the probability that the particle will be at time n, it will be at the value n? That means each step it must have taken a right jump, right? What's the probability of that? Probability to jump to the right is p, each step. So what's the probability it takes n, p to the power n? So we know that value exactly. Now suppose you put m equal to n here. Okay? So if you put m equal to n there, what do you get? Okay, up to this overall prefactor, you get, if I put m equal to n, so n square comes out. So I get 1 minus p minus q square, okay, which is actually 2q. Yeah, because p plus q is 1, so this will be 2q. And I have an n square outside, and I have 8 pqn. So I cancel. So what I get still exponential, but I get something like q over 2p times n. Okay, which is clearly not the right answer, because the exact answer is p to the power n. So this tells you that if I continue this Gaussian form all the way till the end, it will not get the actual answer. Okay, actual answer will be different from the Gaussian. So Gaussian is not valid for the full thing. So when we talk about binomial going to, Gaussian distribution, central limit theorem, yes, it goes to Gaussian, but only over a certain range. Okay, so here the typical range is, so typical value. So there are two scales in this problem. There is a n, which is the, the linear scale mean value is going like that, and there is a square root of n, which is the typical fluctuation around the mean. Okay, so typical, deviations of m from its mean are described very well by this Gaussian form. Okay, but if I look for atypically large fluctuation, like this guy here, it's a very rare configuration, right? Rare fluctuation. So those rare fluctuations are no longer described by the Gaussian distribution. So you have to somehow, write it in a different way to get this part of the curve, left and right, which is when you go far away. When you look at deviations of order n from the mean, large deviations, they are not described by this central Gaussian peak. So for that, you have to calculate the full large deviation function, which Kiran did in a slightly different language. So we can do that. It's very easy to calculate that large deviation function. How do I do that? Because I know that the probability of Mn, this is for 1D random walk, it's very easy to compute. Because suppose I take n plus positive steps in a given configuration, and I take n minus negative steps. So I started from the origin, I arrive at some value m, let's say, okay, after making n jumps. Okay. So in these n jumps, let's say n plus of them are on the positive direction and n minus of them are in the negative direction. So what I have is n plus plus n minus must be equal to total number of steps, n. And obviously, if I say that I have finally arrived at m, so that means number of positive steps minus number of negative steps must be equal to m. So from this you can compute what is n plus. So n plus will be m plus n over 2, and n minus will be n minus m over 2. Okay? So then, what is the probability distribution of this? It's just a binomial number. So I'm choosing n plus out of n steps. How many ways can I do that? Is this many ways. It's like tossing coin basically. And the probability that I have n plus up steps is because each up step, the probability for that happening is p. So therefore, p to the power n plus times q to the power n minus. So it's just a binomial distribution. So this is the exact binomial distribution. So which means this is n factorial divided by n plus factorial, which is n plus m by 2 factorial times n minus m by 2 factorial, e to the power n plus, which is n plus m over 2 times q to the power n minus m over 2. Okay. So now, suppose, so this is the exact formula. This formula is valid. This formula completely for any finite n describes this curve. Okay? But I want to take the large n limit, and I want to look at the fluctuations on a scale which is linear in n. That's the other scale in the problem. So what I should do is I should say, okay, suppose I set m over n to be x. That is, I set m equal to nx. Okay? So I'm asking this probability, but where m is n times x, where x is of order 1. Okay? So that means both m and n large, but their ratio is fixed to be x. So if I do that, then then our old exercise, so here I just put n times 1 plus x over 2 factorial, because m is just nx, and here it's n into 1 minus x by 2 factorial, and x is of order 1. P to the power n into 1 plus x over 2, q to the power n into 1 minus x over 2. Okay? And now you do your usual thing, that is take the n large limit keeping x fixed. You would use this Stirling approximation to this. I won't carry out. And you can actually do it very easily. And you show that this becomes, so this is an exercise. This becomes e to the power n times some function of x, which depends only on x. And remember, this x is just the ratio. So this is a function of m over n. And what is this function? You know all this. Kiran has shown you already. So this function phi of x is just So this is the exact large deviation function. So in the limit when n and m both large, I'm looking for fluctuations of order n. I'm taking the n going to infinity limit. Then this functional form should describe my full curve all the way from here to there. And let's just check. Let's just check this limit here. So now, if I look at m equal to n, that means x equal to 1. So what happens when x equal to 1 in this function? This part is 0. As x tends to 1, so phi of 1 is, so this part is 0, and here this 2 cancels, and you get log of 2 over 2 cancels, so you get minus log p. So when you put it minus log p here, you get e to the power minus n times minus log p, which is precisely p to the power n. And that's what you are expecting. Okay? So you see that if you extend the binomial, if you extend the Gaussian form all the way up to there, you will be wrong because you get a wrong factor. But this large deviation functional form, you can extend over the full range, okay? And it's a smooth function. It describes the two endpoints. You can check that this and that both are given by this function, phi of x. And also, when you are near the mean, that means when m by n approaches the value p minus q, because that's the mean value, okay? So you can expand, so which means x approaches p minus q. So you can plot this function, phi of x. So x is going from minus 1 to plus 1, right? So I'm just dividing this axis by m by n, so it's going from minus 1 to plus 1. And so at the two end, so when x goes to plus 1, this guy phi of x goes to minus log p, and here it goes to minus log q. And in between, it has this kind of convex form with a minimum here, which happens exactly at x equal to p minus q. Okay? And in fact, you can expand around x equal to p minus q. In Taylor series, okay, so if you expand this guy around p minus q, what do you get? You get phi x 1 over 8 pq times x minus p minus q squared plus p minus q 48 p square q square x minus p minus q cube plus etc. Okay. So that means when so it has a quadratic form, very close to the origin, it has a quadratic form, and then it goes to these numbers. This is the full functional form. So if I'm very close to the minimum, okay, that means I'm very close to the mean here, you can throw away this term, and then you see that this guy, so e to the power n phi x, that means e to the power minus n over 8 pq, and x was m by n. So this one gives you back precisely the Gaussian form. Okay? So near its minimum, so large deviation function is a very nice function because it gives you the typical behavior when you expand around its minimum. Okay? So this is the typical behavior over a scale of square root of n. And it also gives you the very large deviations, very far away from the mean. So atypical deviations. So always remember these two words, that is the typical fluctuation and atypical large fluctuation. This is a very nice example which illustrates this point very beautifully. So there is a typical fluctuation of a random variable around its mean. That means if I take a random sample, typically this is the value I'll see. Okay? So in this example, this typical has a behavior like that, where this chi is a typical, order 1 random variable on a scale of square root of n, and it's just described by Gaussian. So typical distribution is Gaussian. Whereas atypical, meaning rare fluctuations around the mean, very big fluctuations, they are overall, you cannot get it from the Gaussian. You have to use the full large deviation function. But the nice thing about the large deviation function is that you don't have to do the typical case separately. It includes the typical fluctuations also by just expanding around its minimum. Okay, so I just keep this little exercise in mind when we discuss this, because you'll be just keep this as a control problem. Just think about this problem when we discuss this, because what we'll see now is that the analog of this Gaussian peak here, typical fluctuations, here it was square root of n order, but in this problem it will be of order n to the power minus 2/3, and this Tracy-Widom, which describes the peak here, is the precise analog of this Gaussian form in this simple toy model. Okay, so this will be the analog of the Tracy-Widom, and these tails here are going to be the analog of the large deviation tails. So we'll see that, but the difference is, apart from the fact that the central peak is not Gaussian but a non-trivial distribution, but there's another big difference, which is that in this problem, you see this full function, the full curve is described by one single large deviation function. There is no, it's a smooth function phi of x. It has absolutely no singularity or non-analytic behavior at any intermediate point, and both left and right large deviations from the mean are described by the same function basically, which will not be the case here. We'll see that the left and right have very different behavior, and actually they correspond to very different physics. Okay, so that is what we are going to see. And how much time do I have? 40 minutes, okay. So 40 minutes will be very rapid. I'll try as much as I can, but you get the flavor of the physics. So this is very important to always keep this example in mind, because this is a very nice, simple toy model example which tells you about typical and atypical large fluctuations. Okay, so and remember this formula also for typical fluctuations. Okay, so now we are back to the random matrix problem. So first thing to calculate that what is the scale here. So like in this problem we had calculated the scale by calculating the variance very easily, and we saw that the variance typical fluctuation is around the mean is square root of n. But here you can't use the variance because it's very difficult to compute. So you want to somehow get an idea of the scale of typical fluctuations around the mean, root 2. So you see, no, but this is lambda max less than W. So in general, if you take W equal to 0, yes. No, if you ask what's the probability that, what's the probability that W is less than 0, that means this part of the curve, okay? So that will be the probability that all the eigenvalues are negative, okay? Which will be the yesterday's calculation. So that's a particular value at this curve. But you want to calculate for general W basically. So remember what is happening. So this is the central picture, which is, so on an average, I have my charges are distributed on the Wigner's semicircle. Okay? You know that this is rho lambda, rho star or rho lambda, whatever. So in the large n limit, my charges are distributed, a typical sample, between minus root 2 and plus root 2. So why, you see why this root 2 is a critical value, because this is exactly the edge of the Wigner's semicircle. And And we'll see that that's why that phase transition occurs in a minute. So if I take from each sample of my charges, each sample of eigenvalues, I diagonalize matrix, I calculate the eigenvalues. Imagine doing numerical simulation, okay? So for each sample, you calculate lambda max, you find out the largest eigenvalue. Of course, it fluctuates from sample to sample. So it's a random variable. So what is its average value? So we know that on an average that system is there. So largest eigenvalue means is the one at the edge here. Okay. So these guys are like point charges. They are distributed like that. So on an average, the largest eigenvalue will be exactly square root of 2 in the large n limit. Okay. By average, then it's just because this is the edge of the semicircle. So what we want to know now is what is the fluctuation around this mean value. So I want to estimate the typical scale of that. How do I do that? Where does this n to the power minus 2/3 comes? It comes from a very simple scaling argument. Okay, and this argument actually, this is a very general argument. It's called the Lipschitz argument. So which is the following. So you said, okay, I want to estimate. So I take any sample, particular configuration, very large n, okay. So the only assumption that goes in here is a self-averaging. So you say, okay, if my sample is very big, roughly speaking, this particular sample will be described by its density will be described by the average density of the full system. Okay, so this is called self-averaging. You know that this is all often happens in statistical mechanical systems. That is, you don't actually have to average over many samples. You just take one big sample, and then it's actually pretty much described by the average thing. So if you have that, so then let's look at, suppose the lambda, the largest eigenvalue is here. So I want to estimate this scale. What's the typical fluctuation of the largest guy? So the idea is you just estimate how many eigenvalues. So you know the average. So self-averaging means I'm assuming that for that particular configuration, my density of states is still given by the Wigner's semicircular law, average value. Of course, there are fluctuations around this also, but I'm ignoring those fluctuations. Okay, I'm saying, okay, for any sample, this is the average density of states. So then I just compute, I take this functional form, I just compute how many eigenvalues are there between, let's say, lambda max, actually typical lambda max, so lambda max typic, and root 2. I'm just estimating here. Okay. So what's the weight of this curve? Just the area under this curve here. It just tells you, because remember rho lambda d lambda is the fraction of eigenvalues between lambda and lambda plus d lambda. Okay. So if I take my lambda max and up to root 2, okay, I know because I cannot go beyond root 2, that's my limit. So in a given sample, my largest eigenvalue may not be exactly root 2, but it will be somewhere here. It will fluctuate around root 2. So I'm just estimating from root 2, and this is the location of lambda max. Okay. So I'm typical. So I'm estimating how many eigenvalues are there in this little this area here. Okay. So that's this integral. So, but you see that this integral, if it is the largest eigenvalue, this is the fraction of eigenvalues. If it is the largest eigenvalue, that means in this interval there is only one eigenvalue. Okay. So therefore, this should be equal to 1 over n. Fraction of eigenvalues that are there in this interval must be equal to 1 over n. Okay. Because this by definition is the largest, that means there cannot be more eigenvalues there. Okay. It's only one, which is this guy itself. So now I substitute this guy here. So lambda max, I just denote by typical value like that. Root 2, 1 over pi, square root of 2 minus lambda square. So lambda max is very close to root 2. Okay. So here you can take lambda to be very close to root 2. So basically what you see when you integrate this guy, okay, you see that this will be roughly root 2 minus up to some factor. Or you can do the integration exactly, but you don't have to do that. I mean just look at what happens when lambda max is very close to root 2. So just do a expansion around root 2, and you find that when you integrate this guy, because this is square root singularity, so that means you can get a 3 by 2 here. So that should be of order 1 over n. Okay. So that tells you that lambda max minus root 2, okay, this is the fluctuation, typically scales like order n to the power minus 2/3. So that means as n increases, this thing is, the spacing is almost going to 0. Lambda max is almost converging on root 2, and this is sort of becoming narrower and narrower and ultimately becoming a delta function. So most of the probability weight is concentrated in the green part of this curve, just like here. Okay? Most of the probability weight is concentrated there. Very small probability at the end, but nevertheless finite probability. Okay? And same thing here. Okay? So I know now the scale of the fluctuation of lambda max, typical fluctuation. So this is the typical So this is exactly the analog of the square root of n, which is the typical Gaussian fluctuation. Okay? So here it was increasing with n, and this guy was going linearly, but here this guy is fixed, and this guy is decreasing with n. Okay? So therefore, just like this, you would expect that the typical fluctuations should be described. So lambda max, so typical fluctuations. Just remember this toy model example. This should be root 2 plus n to the power minus 2/3 times some random variable, which I'll denote by, I don't know what, t, let's say. So this is a random variable. This is the analog of this chi. This chi had a Gaussian distribution, and here the t will have similar form, n independent distribution, p of t. And question is, what is this p of t? So I'm just trying to describe the analog of this Gaussian peak, which is this peak here. Okay? And no. See, this thing is that, I mean, I'm saying again, this is just a, this is just a order of magnitude estimate. I mean, if you are on that side, you just switch the sign. Okay, that's the typical fluctuation around that. Okay, so lambda max can be sometimes bigger than root 2, sometimes less than root 2. Okay, so yes. Because you see, I mean, you are imagine, so P, rho lambda d lambda is what? It's a fraction of eigenvalues between lambda and d plus lambda. So if I'm just looking at the edge, it's the order of magnitude estimate. Okay, if I'm looking at the edge, if I sit myself right on lambda max, I want to look at the deviation between root 2 and this lambda max. How many particles are there between root 2 and lambda max? But lambda max itself is the largest eigenvalue. You cannot have any particle beyond that. Okay. So how many? What's the weight? What's the weight of this curve here? Total weight is 1, right? Because it's normalized to unity. You have n particles, so fraction of particles inside this little width is actually 1 over n, right? So if you are 10 guys, okay, if you look at the maximum guy, what's its fraction? So 1 over 10, right? So you ask, in this class, what's the fraction of, the biggest guy, the tallest guy? Because there is only one tallest guy, okay? So it will be 1 over the number of people in the class, 1 over n, okay? So we want to calculate this P of t, and I won't calculate that. And this was the distribution of the typical fluctuation. This was computed by two mathematicians called Craig Tracy and Harold Widom. And this is a very classic paper in 1994. Okay. So it's a much more complicated function than this simple Gaussian. Okay. So I can write down the form, but I won't prove it because proving it will require a long time. So I'll just write down the result for it. That this t, okay, actually this t, this random variable, it depends on which ensemble you are looking at. So it depends on this beta. Remember this Dyson index beta. Beta equal to 1 is real orthogonal matrix, real symmetric matrix. And so therefore probability that this t beta is less than equal to some number x So this is the cumulative distribution of this guy. So this is equal to f1 of x. I'll first write down and then I'll explain. So 1, 2, 4 corresponds to beta equal to 1, 2, 4, the 3 ensembles. Okay. And these functions are quite complicated function. Okay. So I'll just write down in case I wanted to always keep this Gaussian thing in mind. So what I'm doing now, basically, this is the picture. Forget this. So lambda max fluctuates around root 2, so it has a probability density around this. Okay. This is exactly this curve here. Okay. Around root 2, it fluctuates. And what I'm doing here is to calculate this peak, these typical fluctuations. And this is on a scale of order n to the power minus 2/3. Okay. So that part, the yellow part of the curve, is described by this functional form ddx of that, because this is the derivative. So ddx of that will describe this part of the function once you scale it. Okay. And what is the functional form of this? So, okay, maybe I will not spend time. You can find it in any book or review article. I'll give the reference later on. So these are called Tracy-Widom functions. So they satisfy some kind of differential equations, okay? Non-linear differential equations, which are called Panleve-2 equation. If you don't know about it, don't bother. So they satisfy some kind of non-linear Panleve differential equation, and even to numerically determine them is not so trivial, okay? So what do they look like? So this if I take the derivative of these functions, okay, so I'm plotting f1 prime x, let's say, and f2 prime x, and f4 prime x. So they look like this. I'm just drawing schematically, not really very accurate. So this is beta equal to 4. So beta equal to 2. And you have some other curve which is beta equal to 2. Okay, I'm not writing this is beta equal to 1. Roughly speaking, so they depend on beta and they vary with beta basically. Okay, so I'm plotting f1 prime x, f2 prime x, f4 prime x as a function of x. So they are first of all non-symmetric function around x equal to 0. So they look like Gaussian, but they're not Gaussian. Okay, so they are highly complicated functions. So what you want to know is actually the asymptotics of these functions. Yes, beta equal to 1 to 4. So for other betas, I mean, okay, there have been recent work by Dumas and Virag and other people, but full function is not known. So there's a lot of work in the mathematics literature on this function and also in the physics literature because, okay, let me first write down the asymptotic form and then I'll just discuss about the applications of this function. So it's a derivative, that means the PDF function. So it has this following asymptotic behavior, the tails, this tail and that tail. Okay. So it goes like exponential minus beta over 24 mod x cubed for x going to minus infinity, and exponential minus 2 beta over 3 x to the power 3 over 2 as x going to plus infinity. These highly asymmetric tails. So here on the positive side it decays as a stretched exponential e to the power minus x to the power 3 by 2, whereas on the negative side it decays like e to the power minus mod x cubed with this prefactor here. Okay. So as I said, the derivation of this result is very, very non-trivial. Okay, it requires a lot of mathematical things and it's not a simple Gaussian function. So it's a very weird, function. But the great thing about this function is that in recent, over the last 10, 15 years, somehow this function has popped up in so many different problems. And one example of that Kiran will discuss today, which is if you look at the asymmetric exclusion process, and if you look at the distribution of current, okay? So the distribution of current is precisely described, typical fluctuations of the current are described precisely by the Tracy-Widom distribution. Similarly, if you look at the Kawdar-Parisi-Zhang equation, which is the interface fluctuation problem, which is related to SF, which is also described by the same Tracy-Widom distribution. And it appears many, many other different problems. I mean, I don't have time, unfortunately, combinatorics problems, in so many different problems, it's just incredible. And now it has been measured in experiments. So liquid crystal experiments by Takeuchi and also by fiber laser experiments in the Weizmann group. And so people have found this Tracy-Widom distribution everywhere. Okay. So, and it's not always that you can actually map those problems directly to random matrix problems. But the deep reason is somewhat this Coulomb gas problem, somewhere hidden somewhere. But it's not often obvious. There's no bijection usually from these problems to the random matrix problems. So why the largest eigenvalue of random matrix appears in so many different problems, it's not a priori obvious. Okay. Now, so now we come back to our, so this part is known. So typical fluctuations were known. So now I want to calculate the atypical large fluctuations, because so what I'm done now is the central part here. So this part of the curve I know, or this part of the curve, which is the Tracy-Widom curve. Okay? But I want to know what happens out there. So for instance, I mean, as Anjan was asking, that for instance, if I ask the same question that I was asking for the Gaussian problem, if I ask, what is the probability that lambda max is less than equal to 0, that is W equal to 0. Remember I was asking this question. So this is like analogous to asking in the Gaussian problem, what's the probability that capital M equal to N, let's say. Okay? So what we saw there, that if I ask that rare event, capital M equal to N, I cannot describe it by the central Gaussian form. If I put that, then I'll get a wrong answer. Okay? Same thing here. If I try to extend this Tracy-Widom region, so what I'm asking what's the probability that lambda max is less than equal to 0. That means I have to integrate this curve from minus infinity to 0, right? So this is the PDF. Okay, probability that the lambda max equal to W. So this is the probability density. Probability that lambda max equal to W. So I have to integrate them minus infinity to 0. So that means I'm asking for the area under this curve. Okay. So obviously, if I try to use the Tracy-Widom and put in the Tracy-Widom distribution, okay, this T beta equal to whatever, or 0 or something, I would get a completely wrong answer. Okay. So I have to look for the large derivation functions, just exact analog of the of this case here. But the main difference here is that, see, unlike in the Gaussian problem, here this is root 2, and this typical fluctuations is order n to the power minus 2/3. So I'm asking for atypical large fluctuations which are of order 1. I want to calculate them. So how do I describe them? Okay. So for that, actually, is a much simpler method, which is precisely the Coulomb gas method that I described to you before, is useful. And we can calculate the full large derivation function by working on a scale of order 1 as opposed to working on a scale of order n to the power minus 2/3. The Tracy-Widom is very complicated because you are going on a microscopic scale. You are zooming on this part and then working there. Okay, so it becomes very complicated. But if I want to work on scale 1, then actually it's much simpler, and that's what I want to show you. So but remember this, I'll write it down here, the asymptotics. So this is, I mean, you understand what I'm saying. So I'm saying that this is the probability that T beta equal to X. So it has this asymptotic behavior, which is minus beta over 24 mod x cubed, and so this solution of eigenvalues, again the same thing, 1 over Zn e to the power minus whatever beta n over 2 times this E of lambda I. You remember this. So I want to calculate this cumulative distribution capital P Wn, which is probability that lambda max is less than equal to Wn. So what is this object? By definition, this is 1 over Zn times these integrals all going from minus infinity to W. So this is an exact formula, of course, but this formula is a complicated formula. Okay, so you want to do this integral. So if you do this integral by focusing on this particular regime of order n to the power minus 2/3, you will get residuum. That's how they calculate it. Okay, but we'll not do that. Okay, so we'll work on a scale of order 1 because we want large fluctuations. If we want to work on a scale of order 1, you see that these things n to the power minus 2/3 is almost reduced to a point. Okay, and so we just work on. So we will not get residuum from our Coulomb gas calculation, because for us this regime has shrunk to 0 because we have taken the n going to infinity limit and working on a scale of order 1. Okay, but we will be able to calculate the large deviation function. Okay, so what is the idea? So same thing. So so basically this is the ratio of two partition functions. So there is downstairs, this is just the saddle point density for this is the Wigner semicircular law, and the upstairs I have a problem, same Coulomb gas, but now in presence of a hard wall. Okay, because all my charges are going from minus infinity to W. Okay, they are not allowed to go beyond W. So as if I put a hard wall here. Okay, so I have my Coulomb gas and I have a hard wall. I am looking for all configurations where the charges are to the left of W. Okay, so this is the W. So what you have to do, again you go to this replace this multiple integral by the functional integral, and repeat the same calculation that I did before, and do a saddle point, except that all your integrals should go from minus infinity to W now. So you have an additional parameter which is the presence of the wall W. Okay, and you can calculate the density, and what do you find? So I'll just write down the density. I will not repeat the calculation. So the saddle point density for the numerator. Okay, is the following. Just 1 minute. So again, in the large n limit, it becomes independent of lambda, but it now depends on W. So when you put W equal to infinity, then you see that's the denominator. So when W equal to infinity, the solution is Wigner's semicircular law. Okay? When the wall is at infinity far away, which is the denominator, the solution saddle point density, the equilibrium distribution of charges is Wigner's semicircular law, semicircle. Okay? But now I have deformed it by putting the wall. So it's a different type of deformation than deforming the potential, but it's like a hard wall. So the solution is, it turns out it depends on the value of W. So this solution is Wigner's semicircular law. Okay, so this is this guy here for lambda, with lambda between √2 and minus √2 support, as long as W is bigger than √2. Okay, let me write it down and then I'll explain the meaning of this. But when W becomes less than √2, it changes, and it changes to a different form. which is given by this. Where lambda is between W and minus L of W, and this L of W is given by happens when W is less than √2. Whereas for W bigger than √2, here you have the Wigner's semicircular law. So here the W is here somewhere bigger than √2. So let's think what the physical meaning of this. So you see what happens. Imagine that you start from W equal to infinity. When W is at infinity, so clearly your solution is Wigner's semicircular law because the charges don't fill the wall. Okay, it's very far away. So this integral, it doesn't see the top, upper value of the integral. Okay, as you take W closer, see, as long as W is bigger than √2, these charges really don't fill the W. So they are happy to equilibrate and find their minimum position, which is Wigner's semicircular law. They don't fill the wall at all, okay? Because these things basically gets cut off upper integral at square root of 2 when W is bigger than 2. The contribution from √2 to W is very small here, okay? Till you hit the edge of the semicircle. When W becomes now less than √2, see what you're doing, you are pushing your charge. You are coming like this, you are pushing your charge. When you push your charge, what happens is now the charges reorganize. Okay, they have to find a new minimum, and they reorganize, and they settle down into a configuration like that. So you see, this is like this, and then I push this, and this thing gets modulated here, and a lot of charges line up near the wall, and this end also shifts a little bit, and you have a new charge density which looks like that. Okay. So this is the solution of your saddle point equation, Coulomb gas problem, and your Wigner's semicircular law gets modified to a new form, which is this, which is given by this, and then you do the same exercise. So all you have to do now is to plug the saddle point solution inside the action and evaluate this probability. These two, you have to evaluate. This you already know downstairs. Remember it was e to the power minus beta n squared times whatever 3/4 plus log 2 or something. And you have to calculate this part here and then take the ratio. And once you do that, you get the final answer, which is the following. So probability that, so you see why there's a phase transition. So this is the origin of the phase transition of Robert May. He didn't understand this mechanism, but this is exactly the mechanism basically. He could figure out the critical point, which is √2, which is at the edge of the semicircle. But the mechanism of the phase transition is quite different. And so what you find then, that in the n going to infinity limit, this is given by e to the power minus beta. Let me just be careful and n square of, let me call it phi left of W. This is for W less than √2. And when W is bigger than √2, this is just 1, right? Because the ratio of two partition function both have the Wigner's semicircular law to leading order, this will be basically 1. Okay. So this is the behavior. Okay. And what is this function? You can calculate this function explicitly. So there's a reason for writing this down, and I'll do that in a minute. So let me get rid of this. Calculation, you find that phi left of W is given by 108.36 W square is W fourth minus 15 W plus W cube times square root of W square plus 6. plus 27 log of 18. The reason I am writing down this explicitly will be obvious in a minute. Okay, with w less than root 2. Okay. So this is your large deviation function, and again you see that there is an n square here. So there is a physical interpretation of this, which is just the difference in free energy between denominator and numerator. So this is just the energy needed in order to push this Coulomb gas. Okay. So the extra energy, if it was here, the energy cost is 0 essentially, and you push, and so this is the energy cost, and not free energy cost, because the entropy term is of order n. We have neglected that. It's just the energy cost in pushing. So there is a very nice physical interpretation of this phase transition. You see, this is a phase transition, but this is like the analog of the free energy of the phase transition. Okay, in pushing the Coulomb gas. So now, this has to be w less than root 2. What happens when w goes to root 2? So you take your explicit function, and you can evaluate what happens when w goes to root 2. And it's very easy to check. You can check. This goes to 1 over 6 root 2 times root 2 minus w cube as w goes to root 2. Okay. So what this means, that with this interpretation of free energy, if I take the log of p, which is the analog of the free energy if you like, so that log of p goes like minus of log of p, and you divide by beta if you like. This is minus kbt log z basically. So that goes like, and n square, so you divide by n square, and take the large n limit, then this is this left function of w. So this is a free energy. Okay, so you're plotting this free energy as a function of w. So there's a critical point w, and this free energy goes to 0 to w as you approach root 2 as a third order, the power 3 here. So this means, and beyond that it's actually 0, right? Because beyond that it's 1, so log of this is 0. So it's 0 here, and it's a function which is this phi twiddle of phi left of w. So phi left of w is just a free energy, and it vanishes as a power 3 at the critical point, okay, root 2. So therefore the third derivative of the free energy is discontinuous, because if you take the third derivative from the left, which goes to a constant which is different from 0, on the right hand side is 0. So third derivative is discontinuous of free energy. So that's why it's actually a third order phase transition. So you can give an interpretation of the maze transition now. It's like a thermodynamic phase transition for a long range system, but it's a third order phase transition. So one more nice thing is that if you look at this curve, this functional value here, and just substitute it here, okay, and you see something amazing. So all these results was in this reference I gave you by David Dean and myself, regulator 2006. Anyway, there's a very nice, there's a nice review that we wrote with Gregory Shit. I'll give the reference at the end, and so I know you're getting tired, but I just want to make out one final remark, which is that if I substitute this guy here explicitly, what do you get? You get e to the power minus beta n square times 1 over 6 root 2 times root 2 minus w cube, right? Now you remember the Tracy-Widom variable was root 2. So I was writing that the lambda max, or w if you like, is root 2 plus 1 over root 2 n to the power minus 2/3 into this Tracy-Widom variable x. Okay. So if I reorganize this, so I can write down this as e to the power minus beta. I take the n squared inside this cube thing and write it as n to the power 2/3 times root 2 minus w. I can always do that, okay? And I have a factor 6 root 2, which I'll inside. So Tracy-Widom variable is root 2 minus w on the left side times root 2. So I'll put a root 2 there and divide by root 2. I have 1 over 6 root 2. I'm just rewriting this in terms of the scaled variable. And then you see immediately there's beta, and this root 2 to the power cube comes out basically, and you get a beta over 24 times this root 2 n to the power 2/3 root 2 minus w cube for w less than root 2. So this is the Tracy-Widom value x. So you see that you recover the left tail of the Tracy-Widom, which was precisely this beta over 24, including this factor 24, x cube. So what this means is that what I'm computing here is the left tail, this function, okay? I'm saying that when w approaches root 2, okay? So I'm describing this part of the curve here. So this part of the curve must match to the left asymptotic tail, because scaled variable x going to be infinity minus infinity means you are almost at this tail. So if you come from the Tracy-Widom side, you get this. And if you come from this calculation from this side, it smoothly matches with the left tail of the Tracy-Widom distribution. So in other words, you can say this is a very simple way of calculating the asymptotic tail of the Tracy-Widom distribution. You don't have to go through all this Panlev equation and so on and so forth. And so this is the physics. So physics is that you push the gas. So this phase of Robert May, which is the unstable phase, like W less than root 2. So this is what I will call the pushed Coulomb gas phase. Just one more word and then I'll end. What about the right large deviation function? Well, so far we are describing only this part of the curve. What about the right side here? So this method that I told you yields 1 for the cumulative distribution. That means, I can't describe this part. It's saturating, this Coulomb gas is to large n limit, it's saturating to 1 here. Okay, I can't describe this part. So for that you have to use a different strategy. And I don't have too much time to really talk about that. But basically, instead of looking at the cumulative distribution, main idea is the following. Instead of looking at the cumulative distribution, look at the PDF. So you ask what's the probability that lambda max equal to W, where W is bigger than root 2. Okay. So that means what I'm looking at is typically configuration of the charges which are in the Wigner's semicircular law. Okay. And I'm looking at, so this is root 2. I'm setting one charge at W. So this is the probability that lambda max equal to W. That means you put one charge there at W, and you look at all the other charges. Okay. So it's like almost like, this configuration is almost like taking a charge from the Wigner's semicircle and putting it outside. So you're like pulling a charge. Okay. It's like pulling an electron from Fermi C. In other words, I put this charge and I calculate the energy of this configuration. So this will be e to the power minus beta n by 2 W squared, which is the external Coulomb potential that this charge fills. And then I have to integrate over all the other guys, okay? So when I integrate over all the other n minus 1 guys, I have the Coulomb energy of this charge with the rest of the guys, which is just beta times log W minus all these lambda i's, I going from 1 to n minus 1. And then I have the joint distribution of these n minus 1 charges. Formally, this is the object we are looking at. So by definition, okay, up to some normalization factor, by definition, probability that the largest eigenvalue is W, that means you have to set one eigenvalue at W, and all the other eigenvalues you have to integrate from minus infinity to W, okay? And what you see is that, so this guy comes out, of course, because this is the external harmonic potential that this guy feels, but there's the interaction energy of this guy with the rest of the other guys, which is given by this term, and this term includes all the other interacting charges. So the idea is to now do this object by saddle point method. And when you do that, you see that this guy here, because you've taken out only one charge out of n, and n is large, so the saddle point density of this guy will be essentially, again, the weakness semicircular law. What this tells is that if I take out one charge outside this C, it doesn't really affect the shape of this density here, okay? So therefore, this object here essentially becomes e to the power minus beta n by 2 W square plus beta log, and this you can replace beta in n times log of W minus, and then you have this semicircle density d lambda d lambda. So you just have to calculate the charge that you need to pull out this one charge extra out of the C, and that describes essentially this behavior. And this, there will be e to the power minus n square factor here, which will cancel with the denominator there. So essentially what you have is finally something which is of order n and not n square. So this one goes like e to the power minus, so this is like a standard thermodynamics. So I'll call this function phi plus or phi right of W. And knowing the weakness semicircle, you can do this integral very trivially. And what you find is that the phi plus W or phi right W, I don't know if you can see it here. Oops, I'll write it here. Is just half W square root of W square minus 2 plus log of W minus square root of W square minus 2 over square root of 2. So this is the exact right large derivation function. So to summarize, what I'm saying is, and then I'll finish. So I'm saying that the probability that lambda max equal to W given n, I'm describing this curve here. So this curve has three parts, okay, depending on the location of the W. So if W is less than root 2, it's described by e to the power minus beta n square, and then you have this phi left function, which is given explicitly by that. On the other hand, if W is bigger than root 2, this guy goes like e to the power minus beta n and not n squared, phi of right. And the reason it goes like n and not n squared is because it's just the, you don't affect the rest of the charge. So it's just the cost in pulling out one charge out of n. So therefore it's of order n. It doesn't disturb the other charges. They don't have to reorganize. And that's why it's of order n. And then in between, when W equal to root 2 plus order n to the power minus 2/3, so then in this middle regime is described by the Tracy-Widom function, which is this f beta prime of W minus root 2 times n to the power 2/3 times n to the power 2/3, so that's normalized. Okay. So that's the summary. So this is the Tracy-Widom central part, that's the analog of the Gaussian part here. And unlike in this example, toy example, instead of having one smooth function, here you have very different behavior. On the left, you have e to the minus beta n square phi left, and on the right, phi right. Phi right is this function, and phi left is that function. Okay? So this function was derived by myself and Vargasola. So this was a URL 2009. don't remember the difference. And what you see, and you can, if this is an exercise, you can check that if you take this guy again and approach W going to root 2 and reorganize this, and you will get back the right tail of the Tracy-Widom distribution. So this, the two tail regimes, they match perfectly with the central Tracy-Widom regime. And so the important point is the reason why you have a discontinuity here, like a different functional form on the left and right, is because you have a third order phase transition in the underlying Coulomb gas, okay, which you don't have in the Stoy problem. The Stoy problem is very simple. It's just one single function which includes the central part as well as the large deviations. But here, there's a kind of discontinuity, which is a third order phase transition, and that makes this problem much more interesting and quite nice. And so I think I'll just finish here, and let me just give you, at least whatever I discussed today, you can find in this review here. Just give you the reference. So this was a review by myself and Gregory Scher. And you'll find other references in this review, the ones I have not given you. And actually, you will see from Kiran's talk today, he will also talk about the analogs of this in the SF problem. So it's published in Journal of Statistical Physics, Statistical Mechanics, I think, sometime this year. I don't remember the exact reference. So there you discuss all this different matching and these problems, and you'll see. And in fact, these large deviations, right and left, they have now been measured in the experiments at Weizmann using fiber laser optics, and they can not only measure the central part, but they can actually measure. These are very tiny probabilities, okay? But still, they can measure exactly this phi left and phi right, and they have verified that this formula works very well. So let me just summarize my lectures, and what did I talk? Just a flow chart, basically, not any details. So that you at least remember some words. Mm-hmm. This one here? No, but here this is the leading order n. So if you want the correction terms here, then of course you have to churn out. See, if you are interested in the large n leading term, then the Coulomb gas is a very nice method. Okay. If you want corrections, calculated by Coulomb gas method is very difficult. Actually, people do this. There is some method called loop equation method. Okay, I didn't want to get into the details of that, but the thing is that see all these different techniques. Okay, of course they ultimately have to match, but some of them are suited for finding some regime, where some others are suited for something else. Okay, so calculating the distribution of lambda max in terms of Hermite polynomial. Okay, so that will give you only the central peak, and that's what exactly Tracy and Widom did. It's not as simple as Hermite polynomial, but you have to show that there it satisfies some Parnell equation, and it's very complicated. But basically, it comes from the orthogonal polynomial calculation. Okay, but the orthogonal polynomial calculation, you cannot use again for the large deviation. Okay, it's very hard. You cannot do that because there you have to do the Plancherel, rota asymptotics. Mathematically these are horribly complicated problems. Okay, so the Coulomb gas approach is, for me, it's very nice because it's physical. You actually see what's happening. You have a gas of Coulomb, you just equilibrium stat make. Okay, so you know exactly what you're doing, and you get very cheaply all these complicated mathematical results. Okay, well, you don't get everything, but you get these large deviation things very quickly and very easily. Okay, so just to give you a summary of the flow chart of what I discussed in my lectures, and so that you just remember this flow chart, and any other details you can always read up in the literature. But and I discussed that in order to have real eigenvalues, you have three different types of ensembles, which is real symmetric matrix. So this is the beta equal to 1, real symmetric matrix. Beta equal to 2 is the complex Hermitian matrix, and the beta equal to 4 is this symplectic matrix, Quaternion matrices, sorry, which I did not discuss in the class, but it's a detailed looking. So all these matrices have real spectrum. So this is the Dyson's threefold way. And what we are interested in is for such matrices, if we make the entries random variables, then what can we say about the eigenvalues of such random matrices? Okay? So entries are random variables, and we saw there are two ways of doing that. So either you take all independent entries, so these are so-called Wigner matrices, or you take rotational invariant ensembles, which is physically more appealing from quantum mechanics, because if you change the basis, it should not change the ensemble. And for such rotational invariant ensemble, we could diagonalize this matrix by making an orthogonal transformation. Similarity transformation. And the advantage of rotational invariant ensemble is that you can, the eigenvectors and eigenvalue coordinates, they decouple. So you can, and then you can forget about the eigenvector degrees of freedom, and you can calculate explicitly the joint distribution of the eigenvalues, which we had this form in general. So at this stage, said, okay, we can forget about the random matrix now, okay? We think of this as just charges on a line, and then we do equilibrium stat mech on this problem. But this is a bit unusual system because of this term here, which means a long-range correlation, pair correlation. So the usual standard techniques of equilibrium stat mech in 1D doesn't work. I mean, like transform matrix and so on, which works for Ising model, it doesn't work here. So then we devised a method to at least, so I said, of course, sometimes you can actually calculate things exactly, this multiple integral. So given this, you want to calculate observable properties. And depending on this V of lambda, sometimes for lambda, for simple Gaussian case, quadratic V lambda, you can actually calculate the partition function exactly. This is a Selbach integral, but it's not always very useful because you cannot generalize it to arbitrary V lambda. And on top of that, you cannot calculate the other observable properties just using Selbach integral. Okay? So you needed a method to somehow extract the large n behavior of this. And for finite n, of course, apart from Selbach integral, as I said, there is this very powerful orthogonal polynomial method, but which works only for beta equal to 2. Okay? I mean, there are generalizations for other betas, but those are very complicated mathematics, at least for me. So what we seem to be interested only in the large n limit, okay? So then all we did is to basically replace this multiple integral when you are doing partition function by a functional integral, okay? So and I mentioned that this is a very general thing, so this is by code screening. This you can do for any long-range system. So I discussed the method in detail, and so the advantage of that is that what you have then is a functional integral or field theory or whatever in terms of the density and not in terms of just the individual eigenvalues. Okay, and this typically has this form into some action of rho of lambda, and then you can do saddle point on this. And you can extract the large n behavior of such functional integrals. Okay, and one other point I mentioned, I discussed two types of observables. So in the last class, I discussed linear statistics. That means observable like something like this, where f can be a nonlinear function, but this is always f contains only each of the term contains only one eigenvalue basically. So f of lambda I. This is it's not a function of f of lambda I times lambda j and so on. This is called linear statistics, and for which when we actually put it as a delta function, all it does, it renormalizes the effective potential, it deforms the effective potential, and we can actually use the Jacobi method. So this saddle point we can actually calculate explicitly the solution. That's the most important point here. And once we have that, so then then it just deforms this potential. Therefore, in principle, you can calculate. I showed you one example where you can do this calculation, which is the example of index problem, where f of lambda is just theta of lambda, which means just a is just the number of positive eigenvalues. And today, I discussed another example of another observable, which is lambda max, largest eigenvalue, or minimum, lambda mean if you like. Which is not of this form, and but still one can adopt this Coulomb gas method, just putting a hard wall at the upper limit of the integral and do the same functional integral, same calculation, but keeping this w, and then looking at as a function of w that is the distribution of lambda max. You can compute the large deviation properties. And I also talked about the typical behavior of the lambda max, which is described by the Tracy-Widom distribution. And I mentioned, but I did not have time to discuss, that this Tracy-Widom distribution is universal in the sense it's ubiquitous. That is, it appears in many, many different problems. And in fact, this is one of the frontline areas of research in statistical physics right now. So both a lot of mathematicians as well as physicists are working in these problems. Okay. Because of this reason, that physicists get excited whenever there's some universal function is found, and we don't quite understand very well why this same function appears in so many different problems. And that's why I think it's an exciting and interesting area to work in. And also, not just theory, not just abstract calculation. Now there are real experiments to determine, to measure these objects. I mentioned, I didn't show you, but where you can actually measure this full distribution of lambda max. So I think that constitutes a very exciting, that's why I kept on saying in my first lecture that even though random matrix originally probably came from, in physics, at least from the nuclear physics literature, and nuclear physics may be dead by now, but the random matrix actually lives on, okay? Because depending on the new application, you ask new questions, and you ask find new observable, and so again you have to find out some new techniques to do these calculations, and so it's a very evolving subject, and it's very exciting. So with that, I think I finished my lecture. Thank you very much for all your patience, and.